All right, welcome back everyone. My name is Dustin, and now we're actually going to start working on the asset packager. So the goal for the asset packager will be to take all of our assets, convert them into Lua, and compile them to Lua bytecode, and then package them into a nice zip archive. So when we're converting the assets to Lua, we're going to want to do the conversions of the different types of assets on separate threads to save us some time. Now we could do them one after the other. However, if there's lots of assets to do, it would be a lot faster if we could run all the different types or tasks in parallel. And for that reason, we're going to create the thread pool. A thread pool is a design pattern that manages a fixed number of worker threads, which are reused to execute many tasks, instead of creating and destroying threads for each task. In our case, the tasks are the conversion of the assets. So this will allow for parallel execution of the tasks, which is ideal for handling our assets in the asset packager. Now, we're going to be able to use the thread pool class in other areas as well. However, we have not introduced it into the engine yet, so that's the first thing that we need to do, okay? So let's get into it. All right, so let's open up our code, and we're going to want to create our thread pool in the Scion utilities. That's where I'm going to put it. And this is just going to be a header only file. So add new file. We're just going to call it the thread pool. .h, and we're going to have our pragma once, and let's make this a little bit bigger. Cool. And I want to see something here. I can't remember what the namespace is for this. Just Scion util. So let's grab that namespace Scion util, and we'll paste that in. Awesome. And we're going to have to include a few things here. We're going to need to include the vector. Now we want a vector because we want to hold all the worker threads in a vector. Include the queue. All of our tasks will be stored in a queue. Then we need a thread because we're going to be using different threads. We're going to need a mutex. We're going to need to include the condition variable. We will use a condition variable to signal to the threads that there's work available. And then we're going to need to have a future and functional. And lastly, atomic. We're going to need that for the shutdown flag or the stop flag. So now we can actually create our thread pool class. It's going to be class thread pool. KD. And we're going to have a public section and we're going to have a private section. Okay, so let's add our member variables first. And so the first variable we're going to need is the vector of threads. So creating and destroying threads is expensive, so we'll create a bunch of threads in a pool and use them to run tasks. Okay, so that's going to be std vector std thread. And we'll call this the workers. All right. Then we're going to want to create a queue for the pending tasks. The queue will be of the type std function. So we want to go std queue std function. That'll be just a void tasks. Now we will be accessing the queue from different threads, so we're going to need to prevent data races or other issues. So we're going to have to use a mutex, and we're going to want to use std mutex, and we'll just call this mq mutex. Awesome. And we're also going to be using the condition variable as stated before. Now this will notify the worker threads of new tasks as they're added to the queue. So std condition variable mcondition. Lastly, we're going to need an atomic bool for shutting down the thread pool. This will also prevent the addition of more tasks into the queue and signal that the thread can be finished. So that's std atomic bool mb stopped, or mb, yes, stopped. Awesome. All right, so let's go and create our constructor. So that's going to be explicit thread pool. Now this is going to take in a size t for the thread count. And by default, we're going to have that equal to the CPU's hardware concurrency by going std thread hardware concurrency. Okay. So if we have 8 logical cores, we'll get 8 workers ready to handle our tasks in parallel. And we're just going to do everything in the header file here. Control KD, that down. We're going to initialize our stopped to false, not stopped. So here we're going to loop through our thread count and then place back new threads. So we just want to loop through them all. So size t, I is equal to 0, I less than thread count plus I. And then we want to launch the worker thread and push it or and place it back into our workers vector. Workers dot place back. So each worker thread will run a loop waiting for tasks. It will grab the task off of the shared queue using the condition variable that we created. So this needs to take in this, then it will have a function. It doesn't need to take anything here, so we can leave that empty. And then we'll have inside while true. All right. Right now, we're going to want to create a local variable for the task. This will just be an std function of a void task. That task. Cool. So this will be used to grab the task off of the queue. Now we're going to want to create a separate scope. The reason why I want to create this separate scope is because we're going to use a unique lock. And this will allow us to lock and unlock itself once it leaves the scope. So it'll lock itself here, and then as soon as it leaves the scope, it'll unlock that lock. Okay? std unique lock mq mutex. We need to use the unique lock here to guard access to the queue. This will ensure that no two threads try to modify the queue at the same time. Okay? And once one of the threads acquires this lock, the other threads will wait here until the mutex is free to be acquired by the next thread. Okay? So now we'll need to use our condition variable to tell the worker to sleep until the thread pool is being shut down, or there's at least one task in the queue that could be used. So we're going to want to go condition dot wait. And then we're going to want to pass in the lock. Now the thread must hold this lock when using the wait function. This ensures mutual exclusion when checking or modifying shared data, like the tasks or the task queue. And then we're going to have to send in a function or a predicate function. This means that the conditional wait will wait here until the predicate returns true or the function returns true. So that takes in this. Then we want to return only if it's stopped, MB stopped, or the task queue is not empty. Okay, let's go out a little bit. So what this is doing here is we have our wait. So this thread has acquired the lock. Then it's pushing this lock into the condition variable. And then it's saying, hey, wait here until one of these two returns true. Okay. So if we've made it here, that means that we're either stopping or there are some tasks that we can do. If there's no tasks left and we're stopping, we just want to leave. That will allow us to break this while loop. Okay. So then we can go if mb stopped and mtasks dot empty, then we can just return. Otherwise, we want to grab the next task from the queue. Okay, so we'll go task, when we created above, is equal to std move. We want to actually move that task into the local variable here, tasks dot front. So we're getting the first queue or the first element that's in the queue because that's how you grab it. Then once we do that, we can pop it off the top. mtasks dot pop. So we've already moved it into this task and we can pop it out of the queue so it's no longer in the queue. Okay. And we can go out a bit. Let's go back over here. Awesome. And then right outside of the scope here, the lock will be opened. And then now we can execute the task outside of the lock. And since the lock is now open, the next one inside can actually grab that. The next one that's waiting, that is. So we go task and run it. There we go. And that's it. Then it'll come back to the top and do the same thing over and over again as it can. All right. And that's it for the constructor. Okay, so we have our constructor. And next thing we want to do, we want to make sure that we cannot copy the thread pool. Okay, so we don't want the thread pool to be copyable. We want to delete the copy constructor and the copy assignment operator. So we want to go down here and we want to go thread pool, const thread pool reference equals delete. And then we want to do it for the assignment operator. Thread pool reference operator equals const thread pool reference equals delete. Awesome. So now let's do our destructor. Now, once the pool is destroyed or the thread pool is destroyed, that is where we're going to signal all of the threads to wake up and join before exiting. Okay, this avoids having any dangling threads or access violations. So this is going to signal the shutdown and join all the threads. This will be our destructor, thread pool, and we will set the bool std lock guard lock mq mutex, then mb stopped is equal to true. Now we want to wake up all the worker threads so that they can exit. So we go m condition notify all. Lastly, we need to join all of the threads to ensure a clean shutdown. So we want to go for auto reference thread in m workers right here. Then we go if thread dot joinable, then we'll join thread dot join. Awesome. That is it. That is it for that. So that will handle all of our threads for us. Okay, now the last thing is the enqueue function. This function will allow us to send tasks into the pool and get results back asynchronously. This is going to be a template function that takes in a function and variadic arguments. Okay, so let's do that now. That'll be template, type name func, type name args. That's allow us to have variadic arguments. Okay. Basically, what this is doing is we're enqueuing a task with optional arguments, and the goal is to return a future to get the result. Okay. So here we're going to go auto in queue, and it's going to be func, and then args, and it needs to return std future of std invoke result t of func args. Okay, let's make this bigger. I mean, smaller because we're getting a bit wide. OKD. All right. So what this means is that it can accept any kind of callable, that would be a lambda, function pointer, or functors, along with any number of arguments. Okay. Then we're going to want to return the future here. However, we want to return the result from the function or from the passed in callable as the future type. Now we do this by using the std invoke result t, and then it takes in the function and then the variadic arguments. So what this is doing is basically asking the compiler, if I call this function with these arguments, what does it return? Okay, so that's what it is. So basically we're just setting the future as the return type of the function that we're passing in. This allows us to use any function that we need to use. Okay, so now inside of here, we're going to create an alias for the invoked result so we can pass it into a package task that we're going to create. So we can go using return type equal to std invoke result of the func args. Okay. Now this alias is optional. It just makes the creation of the package task more clear because this is going to have to be the return type for the package task. What is the std packaged task? This is a magical wrapper that takes in a callable like a function or a lambda then runs it when you are ready and gives you an std future of the return type to get the result later. It literally packages the task so you can launch it later and get the output asynchronously. So let's create that now. So we're going to go auto, let's actually make a space here, auto task pointer equal to std make shared std packaged task. That's going to be our return type. And this is a function like that. Okay, so we're making a shared pointer to a packaged task of our specific return type, and that's for the future. We wrap the packaged task in a shared pointer so that multiple systems like the queue or the worker thread can share the ownership. Also, it will automatically be cleaned up once it's no longer used. Okay, so then we're going to want to use std bind to create a new function and bind all of the passed in arguments. Okay, so we go std bind. And then once we're doing the bind, we're going to want to use perfect forwarding using std forward for both the function and the arguments. Now, the reason that we want to do this is because the original function and arguments could be references, R values, consts, etc. And std forward preserves the exact type. This is critical for performance and correctness, especially with move-only types. Without the std forward, we might make unnecessary copies or even fail to compile. Okay, so that's std forward of the func, passing in the func. Oops. Then bring this down again, sorry. And we're going to do another forward as well, and this time for the arguments. std forward. All right. So now that we have the task pointer, let's create a new scope here so that we can lock the task queue before adding in the new tasks. So we can use a lock guard, std lock guard lock of the queue mutex. We're going to want to check to see if we're stopping the queue. So if the queue is stopping, we don't want to allow to add more tasks. Okay. So we're going to want to go if mb stopped. We're going to actually throw here std runtime error thread pool is stopped. Now, if you don't want to throw, you can just have an error here and then just return. Then we're going to want to emplace back or emplace the new task wrapped in a void lambda. M tasks dot emplace. That takes in the task pointer, then a void, and then we're just calling the task. So it takes in this lambda, it captures the pointer, and then inside of the lambda, when the lambda is called or the task is called, it will call this task. Okay. All right. So outside of the scope, now we're going to want to notify one thread that a new task is available. So we're going to go m condition dot notify one. Once that's done, now from the task pointer, we can actually get the future. So we want to go return task pointer get future. It's getting this from our package task here. Okay. All right. And that's it. That's all we need to do for our thread pool. We can't test it out in this video, but we can build just to make sure that it runs. So let's build. Okay, so it built fine. And you know what? We should do a small test, just a small test, and we'll get rid of it. We do want to actually add an alias down here. So let's go outside of here. Let's go using, and I'm going to call this the shared red pool. That's going to equal to an std shared pointer of the Scion util red pool. And that is what we're going to give to our registry. So let's go into our application.cpp and add one to our registry context. Down here, go to our editor, application.cpp. Up at the top, Do we have a scripting one already? Not scripting, a utility one yet? Nope, I don't see one. So we just put it here. So include Scion utilities slash thread.h. We have our thread pool. And let's go down to init app. Here, we will, right here, add it to our main registry. So let's go main registry dot get or add context. And it's going to be the shared thread pool std make shared Scion util thread. And I only want 4 threads for now. Actually, you know what? Let's just do 6. This should return auto the thread. And let's just create a simple vector std vector of std future of int, and we'll call this test futures. And right here, we're going to go the thread pool. Oh, this is happy. Add 2 context. Sorry, guys. In queue. And we're going to want to send in a function and the arguments. And we're going to want to get the future from that. So go auto F1. Or actually, let's just go test futures dot in place back. Turn 17. Another one. Then this one will be for auto shoot and test futures. Test. Oh wait, no. Let's just go Scion log. Sure. Shoot.get. All right, let's see if that works. So we'll run it. So it should have, oh, we got some failures here. See. All right, so I'm just going to open up any project. I already got this one set up. Open it. Let's check our logs. There it is. So it did work perfect. What you see here is we have the 17 that we added in and the 15, that's the 7 plus 8. Awesome. So our futures are working, our thread pool is working, and that's it for this video. In the next video, we're going to actually add this to our asset packager. So we're going to create the asset packager class, and we're going to start actually packaging the assets on using this thread pool on different threads. Okay, so that's it. Make sure if you to like, comment, and subscribe if you haven't done so already. If you have any questions or concerns, please leave them in the comments below. And that's it. All right, take it easy.